Okay, now roughly 2/3 of the class, actually, in this case, exactly 2/3. And let's see if I can. Okay. Solve the second equation by putting everything over common denominator. Okay. That's very good, and that was well done. I didn't check every detail of every step because I didn't want to hover over your shoulder forever. But I saw the process and I didn't see anything that didn't look correct. So that could be done correctly. All right. If you do, I think you end up with a quadratic equation. So I know at least one person ended up with a linear equation, which is really nice, which is what you do if that x wasn't there. So maybe that x got lost or something. But again, the process was fine. Okay, well, we'll get to this one in a minute. I wanted to comment. You don't need to do that. I'll show you why. Let's first do this, okay? So let's say we have x minus 3 over x plus 12 equals 18. Okay. Now, I'm going to discuss this just briefly. So we can say, okay, we got a denominator. Let's multiply both sides by the thing. Okay. Put it in the form of mathematical language. Okay. So we multiply both sides by the denominator. That makes it multiply x plus 12 times x minus 3 over x plus 12. And that's going to be equal, I have to write around this, but that's going to be equal to x plus 12 times 18. Okay. Now, one thing we should note is that x can't be equal to 12 if we do negative 12 if we do that. Okay. Because if x is negative 12, we just multiply both sides by 0. Yeah, sure, it's equal, but now we don't get any information. Okay, well, again, belaboring this step. We rearrange the x plus 12 over the x plus 12 instead of just crossing things out, and we get 18x plus going to be 108, that's 204. 180 plus that's 206. Plus 36, it's 180, it's 216. That can't be right because that would be 6 cubed. What's the matter with my brain? 180 and 36 is 216. That's 2. Okay, well, anyhow, if that's right, that bothered me a little bit.
Yeah, you're right.
There's somebody out in the hall. Okay, I just got the confirmation I was right. Had to be right. I know 180 plus 36 is 216. What's confusing me is that's a cube of 6. But of course, the cube of 6 is going to have 3 2s, 3 3s in it. And we got 3 2s from 18, from 12, 2 2s from 12, 1 2 from 18. If we break it down, do prime factorization. And we have then 2 3s and 1 3 here. So we got 3 sixes. Okay, well. It's not particularly important, but looking at factorizations is a good thing to do because we've got to look at factorizations when you do these rational functions. Okay. Anyhow, back to the actual problem. This is a very simple step. Not trying to make it more complicated by doing this, just trying to avoid people crossing out this X and crossing out that X. Okay, as people do it all the time. Y'all aren't doing it, but I don't want to make sure we understand the fact. Okay, so this is just X minus 3, because that's a 1 and that's a 1. 1 times that and 1 divided into it. If you do understand that. So that's 18x plus 216. And then we know how to add and subtract on both sides. We get negative 17x equals 219. Actually, it's negative 219 over 17. I think 219 isn't prime, it's got a factor of 3, which gives us 73. 17 doesn't go into 73. So that's the lowest terms. Okay. Now, let's go to this equation. Out of there. So let's say we've got that's just our equation. Okay. Our first step, we can put this over denominator x minus 6, x plus 12 times x minus 6. And this over the denominator x minus 6 times x plus 12. And some people did that and did it correctly. Okay. So we could have done that, but I don't have enough room to do that and comment on it, so I'm not going to bother. I'll show you what's easy. Okay. And the easier thing here, and again, if you did that, it can work if you did everything correctly. But it's much easier. Notice we got denominators, multiply both sides by all of them. So we multiply both sides by both sides by the common denominator. Okay. And x plus 12 times x minus 6 contains this denominator. It is equal to this denominator, and it contains both of these denominators. So it is a common denominator, and it is the least common denominator. If we had any less here, we wouldn't contain this. Okay. If you want to use a bigger denominator, you can do that, but it's going to make things messy. So we do want to do the least common denominator if possible. If we can recognize it. Okay. Well, on the right-hand side, what we get is very easy. just x minus 15, because of course, this can be put over this. So they divide out and give us 1 and all that stuff. So there's our x minus 15. Over here, we have, I'm gonna take a little bit of liberty. Well, we're using a distributive law. We distribute this through subtraction. And there we have it. Again, writing out the steps for emphasis. I can rearrange this expression as I have here. And we notice that we still have the same numerator. We still have an x plus 12 times an x minus 6 times a 3. And we still have the same denominator as x plus 12. But now we've got the x plus 12 over x plus 12, and that gives us 1, and so on. And then we could rewrite this as write this with the x minus 6 over the x minus 6. And again, the numerator still has all the same factors, and the denominator has the same factors, so they're identical. And now this is a 1, and this is a 1. I don't cross them out. I just know that that's 1, that's 1. I've got 1s here. It's very clear that I have x minus 6 times 3 minus quantity x plus 12 times 14x equals x minus 15. At this point, go ahead and use the distributive law. We get 3x minus 18 minus the quantity 14x squared plus 12 times 14 is 168 x equals x minus 15. Then we distribute the negative sign. Like this. And then we recognize it's a quadratic equation. Because we got the x squared here, we got x's, and we got numbers. So we put it in the form of a quadratic equation. Everybody knows how to do this. Going to subtract x from both sides, which will leave us 2. Well, we got 3x minus 168x, which would be negative 165x. Subtract another, we have 164x. So we're going to have negative 166x. From numbers, we got negative 18, we're going to add 15, so we're going to have minus 3. And for x squared, we have negative 14x squared. Now, as you know, it's not impossible to make some kind of arithmetic error, but we understand the process. So once we see the quadratic equation, why do we do this? We do this because now we can use the quadratic formula. Another thing you might want to do, all these signs are negative, so we can multiply through by -1. And we could have all these signs positive, which makes it a little easier to apply the quadratic formula. Okay, now we have then 4 times 14 times 3. I guess I can write all that out. Barely have enough room. All that over 2 times 14. And then you go to your calculator. Okay. Now 166 squared, 4/3, 5/3, 25/9. Approximately 2.8. So that's probably about 28,000. That's pretty insignificant compared to this. So I'm not going to speculate until that comes out. But this is not going to differ from 166 by a whole lot. You're going to have one solution is kind of close to 0, another solution is kind of close to what, 333 divided by 28, about over 13. Okay. That's not important. You know, these numbers are randomized. This is a mess. I mean, it's not a mess. It's very organized and very simple. It's just you're going to have to use your calculator to evaluate. Okay. So I'm not even going to attempt to evaluate that. You're not going to do that in your head. There's not much point me doing in my head, except maybe to check it. So I said maybe x is 12 or 13. If x was 12, of course, we'd have 3/24, which is going to be small. 14 times 12 is 168 over 6, and give us about -20. 68 over 6. -28. Okay. And here we're going to get like nothing like -28. So okay, I'm not going to do that. There's probably a mistake in the arithmetic, but there's the process. Now, what 2 people out of 3 did was put all this over common denominator. Now, I wrote out a lot of steps here, but some of the steps are pretty trivial. Okay, after we write this, well, then we distribute. And you don't really have to write out this step. So you can get from here to here to here pretty quickly. You basically just have to write it out. You don't really have to write this stuff out. You quickly get to this step. And then from here down to here. Pretty straightforward. It's a lot more trouble, even though it might not look like it, to put all this over common denominator, because then you have to recognize that, okay, I've still got the same denominator on both sides. Those denominators are equal. The numerators have to be equal. Okay. So if I had, well, I'm not going to take time to do that. Bottom line, if you got denominators, get rid of them. Except that you do want to write out this step that I didn't want to bother with. X can't be equal to -12 or 6. Same reason. It couldn't have been equal to -12 here. because that would make, that would give you 0 equals 0, and you don't get any information out of that. Okay. Fortunately, when we got down here, we didn't get -12 and we didn't get 6 out of the solution. If we'd have gotten a -12 or a 6 down here, and it's possible we could have, then we'd have to discard any solution that included -12 or 6, because it wouldn't be in the domain of this expression. X is -12. This isn't a valid expression. If X is equal to 6, it doesn't become a valid expression, meaning you have divisions by 0 and you just can't divide by 0. Now that's a kind of a finer point that people tend to lose track of. And it's something that can kind of bite you later on. It wouldn't cause you to fail the course, but it might cause you to get an erroneous solution, cost you a few points. Or if you were trying to apply it in the real world, you get a bad solution, take it to the boss and they fire you. Okay, well, that wouldn't happen. You'd have egg in your face, okay? And you could crash that spacecraft into Mars instead of orbiting. Okay. Everybody wants to be a rocket scientist, right? It's your ambition. Okay, well, some of you have guilty look there. Maybe that is your ambition, but maybe you're just kind of smiling at the fact that no, I don't want to be a rocket scientist. Okay. There are probably more fun things to do unless you're really into rockets. Then it's pretty cool. Okay, we're talking about exponential functions. Our basic exponential function is y equals 2 to the x. Why have I been beating on that in pre-calculus? Okay, again, not everybody is taking pre-calculus right now. So let's be careful, make sure we remember what we learned back 2 months ago about our toolkit functions. The exponential function y equals 2 to the x. You might want to review that so you have perspective. If you're in pre-calculus, you've seen it a number of times. Okay, so we make our table. Remember our table in this course, standard x values are -2, -1, -1/2, 0, 1/2, 1, and 2. I cross out -1/2 and 1/2 because we can't calculate that. You don't know how to calculate it. I know how to calculate it, but it's a little bit complicated. You kind of use calculus to do it. So I can't ask you to calculate that. And we want to be able to understand these functions without access to a calculator, without the use of a calculator. Remember, I require you to be able to show how these calculations work. We're not going to go over that again, but 2 to the -2 means 1/2 squared, which is 1/4. 2 to the -1 means 1/2 to the 1, which is 1/2. 2 to the 0 is 1, any number to the 0 power is 1. 2 to the 1 is 2, 2 to the second is 4. Now we have a table. It's very easy to graph. It's one of the simplest graphs. I consider it probably the simplest of all the graphs of the toolkit functions. Unless maybe you talk about y equals x as a toolkit function. Okay. I don't need to really talk about that because it's so simple. You understand the other toolkit functions, certainly you understand that. Okay. So here's our graph. And we understand here's -2, here's 2, here's 0, here's 4. Doesn't really matter what the numbers are down here. An increasing exponential function is going to have this shape, and we can put any numbers on the x-axis we want, any numbers on the y-axis. That just corresponds to transformations. So every exponential function that's increasing with an asymptote of the x-axis looks like this. Okay, just like every parabola, no matter where you put it, no matter where you transform it, turn it upside down, shift it, stretch it. Okay, now it still looks like a parabola. Okay, variations of the exponential function. It could have a graph looks like this. Reflected through the y-axis. Okay. You could have a graph that looks like this with an asymptote. Oh, however, that's just a vertical stretch, right? You could have one that's like this. And where you exponentially approach whatever this y value is. Okay. So that's what the graph looks like. And you should understand I use transformations to get these graphs. Okay. You'll see examples. Y equals b to the x with b greater than 1 has a graph that looks like this. Whatever b is, if this is 1, this is b. So for the graph I just drew, what's it look like the value of b is? Idea. Okay. So let's say this is a graph of b to the x, b is greater than 1. Well, if 1 is here, then b to the 1 is b, so that b has to be here. Okay. Whatever b is, the graph is going to look like this. What's the value of b for this graph? Well, what are the coordinates of this point? This point is y-intercept. It's 0 b to the 0. You plug in 0 for x and you get the y coordinate. This point here is always 0, 1. So I could, okay, everywhere on this line, just y equals 1. Okay, now given that, what do you estimate the value of b is? Write down your estimate. That's 1 on the y-axis. What's that? Just write down a number. Circle. If you tell me it's 100, I'm going to say no. Okay. Okay. Yeah. Answers ranging from 1.5 to 2. And when I look at it from here, it looks like it's a little less than 2. So 1.5 is reasonable. It's pretty close to 2, so 2 is reasonable. Oh,
Yeah, that's all I was gonna say.
What I was recording, what I wasn't. Okay. Okay, anyhow. If this is 1, this is a little shy of 2. The estimates we got were between 1.5 and 2. So they're all good estimates. So I'm going to say it looks like B is approximately 1.8. So now this is the graph. Y equals B to the 1.8 power. So you could estimate what's B to the second power. Okay, what's B squared? And well, you could easily square 1.8 is 3.24. But you could go up 2 here, come up to the graph, and as it's about there, it's 1, 2, 3. It's a little over 3 lengths. Pretty good. I nailed that. You believe me? Okay. Can you sketch a graph of come out? Let's see. We're going to have a planet of time, so I'm going to go on. Okay. There's a graph. Sketch a graph that looks something like this. Put 1 about there and tell me what you think the value of B is. And I'll remind you that the y-intercept is 0, 1. What are you going to put x equals 1 back? Well, that's your y-intercept, x equals 1. You're going to have 1 on the x-axis. You don't want to go too far because it'll be down there on the axis. But anyway. B is greater than 1 on here. Certainly greater than 1 here. Is what a value see what the value is here. That tells you what B wants. Okay. So here we have a graph represents y equals b to the x. Here's 1. Here's the 0.01. That's getting a good projection line there. But so right here is the value of y equals b to the 1. Here's 1. Here's your graph. Here's your y coordinate. And of course, that's b. Looks like b. In my case, it's about 1/2. Somebody else estimated 1/4. Somebody else graph was a little bit lower, and the 1 was a little further out. You could have gotten 0.2 or 0.3. Okay, if you put the 1 close here, you're going to get 0.7 or 0.8 maybe. But it's going to be less than 1 because clearly wherever you put 1, b is going to be less than 1. Okay, so b has to be less than 1 because the graph is decreasing. So now we see what a graph looks like if b is greater than 1, what a graph looks like if b is less than 1. Well, that's important. Now let's, there's a lot I'd like to talk about. but we'll give you something that'll help you get a good start on the assignment. So incidentally, now notice that this graph looks just like this graph, right? And this graph looks just like this graph switched around. It's just we've kind of relabeled the X and the Y axes, right? Really, we've just relabeled the X axis. That's not important to remember that connection with the basic exponential function. Now, I don't know if I'm recording or not. I'm recording. Yeah, I'm recording. Okay. I don't know why I keep losing track of that this morning. Okay. Because I love to talk about exponential functions. Who cares about the camera? Okay. Y equals b to the x. Y equals 6 when x equals 2. Can you give me the value of b? Turn the camera off. Let you work for a minute. Okay, so this is fairly straightforward. You know that y equals 6 when x equals 2. So 6 equals b squared, right? And b plus or minus the square root of 6. B can't be negative, so b is the square root of 6, which is approximately 2.45. Question mark in my estimate there, might be 4.446. Okay, kind of think it's 4.5. 2.4 is first, 5.7, 6.5, 6.25. Pretty much halfway between, and you don't have a lot of curvature. Anyhow, there it is. And all that stuff I just mumbled is stuff you could understand based on the basic functions, but we're not going to put people in the mental approximations. Okay. So now B is what we call the growth factor. And the growth rate, well, I want to motivate that. Suppose you have $1,000 and 5% interest. Well, in a year, your interest is gonna be 5% of $1,000. It'll be $50. Okay, the easier way to get that. If you factor out $1,000, you end up with 1 plus 0.05. And that's 1.05. So this is the same as 1.05 times $1,000. In this case, then 0.05 is your growth rate. In other words, if you have $1,000 and it's safe, you can make a safe investment at 8%. That's a pretty good growth rate. That just about matches inflation these days. Okay. And of course, you look at inflation, inflation is growing at a rate of 8%. Okay, so the growth rate would be 8% or 0.08. .05 is your growth factor. A factor is something you multiply by something else. Well, I just said that B is called what we call the growth factor, and this relates the growth factor to the growth rate. Calculate what your investment would be worth after a number of years. Well, every year we get to multiply by 1.05. So if we wanted the value after 2 years, we multiply by 1.05 again. So be multiplying 1.05 by 1.05 by 1,000, that'd be 1.05 squared. If we do another year, we'd multiply that by 1.05, giving us a 1.05 cubed. If t is the number of years, then 1.05 to the t is what you multiply by $1,000. What's a graph of $1,000 times 1.05 to the t look like? Small boards. Use this. Okay, so let's just look at this. Let's say we got P of t equals $1,000 times 1.05 to the t. Make a graph of this. Here's one. And we'll say here's one. Actually, we're going to make that 1,000 because we want our money to grow a lot. We don't have a lot of room for it to grow. Of course, it's going to take a lot of years. Okay, so we have $1,000, and here's one. Okay. When t is 1, this is going to be 1,050. Now, if there's thousands here, I'm going to put 1,000 here. So 2,000 would be up about here. And 1,500 would be here. And 11, 12, 13, 14, 1,500. Okay, this point's going to be just a little higher than this one. It's going to have an exponential function. Comes in, goes through here. It's going to be a pretty gradual increase. It's going to take a lot of years to reach $2,000 because the value of 1 is not all that much higher in this graph than the value at 0. Okay. Still, it's exponential. Over here, it approaches 0. Over here, it keeps getting steeper and steeper. Pretty soon, it starts taking off. It turns out that in about 14 years, we're going to double. So 14 years from now, at 5%, even though you only get $50 the first year, you're going to double in 14 years. Okay, well, that's an important process. That's an important part of the exponential function. Now we're out of time. That gives you some introduction. So see what you can do with the assignment. Okay. It mainly uses these functions and then things that you already know. Like one of the first early problems is what's the rate of change of this function between 2 points. Now, rate of change and growth rate are two different things. Rate of change is the change in the value divided by the change in the time, right? Okay. Go back to the assignment and average rate of change we had early in the course. So you kind of need to do that. But I think the Open Math videos do a good job on this. So see how far you can get with this one.